polynomials. Hermite polynomials are defined by Laplace and later studied in detail by Chebyshev. In mathematics, Hermite polynomials are a classical orthogonal polynomial sequence. What is this classical orthogonal polynomial sequence? It is a family of polynomials such that any two different polynomials in the sequence are orthogonal to each other under some inner product. What is this inner product? Inner product is given by fg, which is integral over x1 to x2 f of x g of x into w of x dx. W of x is called weight function. It is also called non-negative function. With support on some interval x1 to x2 in the real line, where x1 equal to minus infinity and x2 equal to infinity are also allowed. There are two different ways of standardizing the Hermite polynomials. Those are probabilistic Hermite polynomials are given by Hen of x equal to minus 1 whole power n e power x square by 2 into nth derivative of e power minus x square by 2, which is also equal to x minus d by dx of whole power n. And the other one is the physics Hermite polynomials. Which is Hn of x equal to minus 1 whole power n e power x square by 2 into nth derivative of e power minus x square by 2, which we can also write as 2x minus d by dx whole power n. These two functions are not identical. Each one is rescaling of one other. That means Hn of x equal to 2 power n by 2 Hen of root x, and also He of x equal to 2 power minus n by 2 Hn of x by root 2. Polynomials arise in probability such as Edgeworth series and in physics where they give rise to eigenstates of quantum harmonic oscillators. And next comes to properties. Properties of Hermite polynomials. Orthogonality. Hn of x and Hen of x are n degree polynomials for n equal to 0, 1, 2, 3, so on. These are orthogonal with respect to weight functions. W of x equal to e power minus x square by 2 for He, and W of x equal to e power minus x square for H. That is minus infinity infinity sum Hn of x into W of x dx equal to 0 for m not equal to n. Furthermore, minus infinity infinity Hem of x Hn of x e power minus x square by 2 dx, which is equal to root 2 pi n factorial delta mn. This is for probabilities. And minus infinity infinity integral Hn of x e power minus x square dx equal to root pi 2 power n factorial delta nm, and this is for physicists. The polynomials are thus orthogonal with respect to standard normal probability density functions. Next comes to recursive relation. The H polynomials are H not equal to 1, H1 equal to 2x with the recursive relation Hn plus 1 of x equal to 2x hn of x minus 2n hn minus 1 of x, and they satisfy a differential equation hn double dash minus 2x hn dash plus 2n hn equal to 0. The he polynomials are he equal to 0, he1 equal to x with recursive relation hen plus 1 equal to x hen minus n hen minus 1, and they satisfy a differential equation hen double dash minus x hen dash plus n hen equal to 0. Next comes to generating function. The Hermite polynomials are given by exponential generating function, that is e power xt minus half t square equal to n equal to 0 to infinity summation hen of x t power n factorial. This is for probabilis. And next, e power 2xt minus t square equal to summation over n equal to 0 to infinity hn of x t power n by n factorial, and this is given by physics. A relation of Hermite polynomials to other functions. Legere polynomials. The Hermite polynomials can be expressed as a special case of Legere polynomials. That is, h2n of x equal to minus 4 whole power n into n factorial into ln of x square whole power minus half. And there is also another h2n plus 1 of x equal to 2 into minus 4 whole power n factorial into x and into ln of x square whole power half. There are also applications of Hermite polynomials. They are Hermite functions, and Hermite functions are agent function of Fourier transform. Hermite functions are represented as phi n of x. Last topic, we have seen the relation between Legere polynomial and Hermite polynomials. In mathematics, Legere polynomials named after Edmond Legere are solutions of Legere equations, that is xy double dash plus 1 minus x into y dash plus ny equal to 0, which is a second order linear differential equation. This equation has non-singular solution only if n is non-negative. More generally, the name Legere polynomials is used for a solution of xy double dash plus alpha plus 1 minus x into y dash plus ny equal to 0. This is more generalized Legere polynomials. Till now, we have seen these are used for so-and-so solution of some equations. Now here what are Legere polynomials? Legere polynomials are ln of x equal to summation k equal to 0 to n minus 1 whole power k by k factorial nck x power k. This is binomial coefficients. Now next topic is moment of inertia matrix. Angular moment of a body can be obtained from the sum of angular momentum of the particles forming the body, that is h equal to summation li. We know that li is ri cross pi. Here pi is momentum, which is nothing but mvi. On substituting, we get this equation, and we also know that vi equal to omega I cross ri. On substituting this, we get this equation, and we also know that ri is the position vector of the particle, which is xi, yi and zi, and w is the angular velocity vector of the rigid body, which is omega x, omega y, omega z. And on substituting, we get this equation, and we also know that cross product of omega I and ri, we end up getting this equation like this. Assuming omega y z I minus omega z yi equal to a, and so on like b and c, we get this equations, and again cross product of ri cross omega I cross ri, we end up getting this equation. By solving this, we get this equation, and separating all the terms, we get like this. summation mi of yi square plus zi square and minus summation mi xi yi and minus summation mi xi zi, so on like this. And taking ixx is equal to summation I mi y square plus zi square and iyy equal to summation I mi xi square plus zi square and izz equal to summation I mi xi square plus yi square and ixy equal to yix. On seeing this above equation, we get summation ii xi yi mi, so on, like we get even ixz and izx also. Similarly, we get iyz and izy. Substituting ixx, iyy, all these equations, we get h equal to ixx, ixy, ixz, iyx, iyy, iyz, izx, izy, izz into omega x, omega y, omega z, which in turn we get I omega. Here I equal to ixx, this matrix, and we know that I matrix is also called moment of inertia matrix. The diagonal elements ixx, iyy and izz are called moments of inertia. The others, such as ixy, iyz, izx, so on, are called products of inertia. This matrix is symmetric. Yeah, there was a negative over here because there is a negative over here, so we get negative. I forgot to mention it. The next topic, use of Hamiltonian and Lagrangian mechanics to explain rocket dynamics. Considering Earth and rocket, let rocket moving with velocity v be q naught, and assuming rocket is at a distance q from the Earth at some instant, we know that kinetic energy of rocket equal to half m q dot whole square, where mass is at that instant. And we also know that potential energy of rocket would be mgq. And from Lagrange's mechanics, we know that L equal to k minus u, which is half m q dot whole square minus mgq. And we also know that from Lagrange's mechanics, d by dt of dou L by dou q naught minus dou L by dou q equal to 0. Substituting the L equation in the above equation, we get d by dt of dou L by dou q dot equal to dm by dt q dot plus m q dot dot, and dou L by dou q would be minus mg. Substituting equation 2 and 1 in 3, we get dm by dt q dot plus m q dot dot equal to minus mg. We know that h equal to k plus u, which is half m q dot square plus mgq. And we also know that Hamiltonian equation, that is d pi by dt minus equal to minus dou h by dou q. But we know that p equal to dou L by dou q dot, which is equal to mq dot, and dp by dt will get dm by dt q dot plus mq dot dot. Dou h by dou q would be mg. Substituting equation 4, 5 and 6, we get dm by dt into q dot plus mq dot dot equal to minus mg. This is the equation of a rocket. Equation of rocket using both Hamiltonian and Lagrange's.